you have a worksheet. We actually started the chapter, so we're only doing 4 sections. This is the last one out of the 4, clearly because it's 2-4. The first section we actually started with a very similar problem, or almost exactly the same problem. I'm going to open up a sheet that we looked at. I've got a bunch of stuff. See if I can find it quick. That you guys explored the different slopes, secant slopes. You have intersecting it twice, or we could have the average up there. Really, it's just the slope. It's like the average rate of change as it gets closer and closer. Does that look familiar? Remember doing that? So slope for the first one, I think it was like 82. And then wait, the 2 points get a little closer, and it was like, that was your group. Do you remember what you got? Maybe like 68. And then they got a little closer and a little closer. Anybody remember what they approached? And then we realized it was getting really, really close to 64. And we talked about how do you get the slope at that exact, yeah, I actually wrote them up on the board again. These aren't from like way back when. Oh, I couldn't remember. I was trying to write up what I remembered. So it's like, and we had those up on the board. You can see they're getting closer and closer to 64, just trying to help jog your memory. So we have all these secant slopes, these average rate of changes, but they're getting really close to one single point where we can get the slope at that instant. And that's our tangent slope, intersects once, or our instantaneous rate of change, our rate of change at that particular moment. So instead of saying, what was your average speed from 0 to 60? And saying, okay, well, in 4 seconds, I went 0 to 60, so 60 divided by 4. We say, what was your exact speed at this time? And that's kind of what this was helping us for. I've got another one. Let's see, a little Java action here. Make this bigger. That shows us both. So what we're saying is, I want that. I'm colorblind. What color is this line? Green? Gray?
Looks black.
Gray? I was thinking gray, but I'm thinking maybe it's green because I maybe wouldn't even be able to tell. So I have this gray line that is my point, like my tangent slope. So you can see that gray line intersects that at just the one point, just barely grazes it. That's a tangent line. That's going to give us our rate at an instant. And what we're going to do is we're going to say, can zoom in a little bit here. What we're going to say is, okay, those two lines clearly don't have the same slope, right? Let's move this so I can approach it a little bit better. Closer. And as I find that average rate of change here, actually that's already pretty close, isn't it? The slopes are getting pretty close. And maybe I don't have the tangent slope, but by getting really close, wow, it looks like I'm really close to 1. In this lower left-hand corner, it's hard for you guys to see, but there's a slope happening here for this red line. And as those 2 points get closer and closer together, the closer and closer the lines are to just be in the same line with the same slope. And so that's how we find the slope at one single point. It's a limit. The limit as this yellow dot gets closer and closer to the blue dot. Cool? And so that's what we're going to try to pull off with these first couple examples from 2-4, which we've talked about before. We've kind of been building up to this point. Average. So this is secant slope, or it's the average rate of change. Remember how we did the average? The secant slope? You have 2 points. Just do your slope formula. We wrote it just a little bit different here. Do that so I can turn the pen on. Slope formula. y2 minus y1 over x2 minus x1. If we look this up in our calc book, and when we see the definition of when we go to like our fundamental theorem of calculus uses this, some different things, our mean value theorem, we might see something that looks a little different. Instead of y2, we'd say like, okay, f of b. Instead of y1, we'd see f of a. And instead of x2 and x1, we'd see b minus a. And what we're looking at is that single point, a, f of a, getting closer and closer to the second point, b, f of b. But right now, they're not exactly on top of each other. We can just use that to find the average rate of change. And for something like this, it's not really that hard then. What's f of b? Plug it in. 3 cubed is 27 minus 3 is 24. F of a, plug in a. 1 cubed is 1 minus 1 is 0 over 3 minus 1, or 24 over 2 gets you 12. If we had a label, if we knew it was miles per hour or like inches per second, whatever we were using that for, we could label that. It's just going to be some type of rise over run type of label though. Pretty easy. We actually did that first section, so that's not even new. Finding slope and tangent line. So this is where we're going to look for it at a specific point. And I'll show you that probably this one last time again, where what we're going to say is we have a point on this graph, and we can graph this. We got 1 square, you get 1. 2 squared, you get 2, 3, 4. 3 squared, you get 5, 6, 7, 8, way up there. So we have this graph. We're looking at this point, 2, 4. And we want to know what the slope is at that particular instance. So what I'm looking for is the slope of a line that just kind of grazes right past that point. That's what we're looking for, the slope of the tangent line, which you can't find a slope if you just have the one point. I can't just say, hey, 2, 4, what's the point? It could be lots of different things. So what we're going to do is we're going to pick a second point a little bit farther away. What do we call that? If that's just a little bit to the right, what do I know about the coordinates of that point? What do I know about the x value at that point? It's bigger than 2, right? The y value is bigger than 4. It just gets a little bit bigger. So what we're going to do is we're going to say, maybe give myself a little bit more room here, that point is going to be 2 plus a little bit. And now I'm going to use h. I've been using a. The book uses h a lot of times for those definitions, so I'll use h. And then what's your y value if our x value is 2 plus h? 4 plus h? You don't have to have the change same height and run change. We basically plug that into our function, so I'll just call it f of 2 plus h. But we could figure that out. Do you know what 2 plus h squared is? Isn't that how you get your y? You plug that in. So we could square 2 plus h. You want to do that? What's 2 plus h squared? 2 plus h squared. You guys know the trick for that, or do we have to just multiply all that out? Anyone just know the answer? It's not 4 plus h squared. That's if it was times. So you have to either multiply or square each and then double them what you get when you multiply it together. Or maybe you don't need to remember that, and we'll just do this real quick. So we'll end up with 4. You'll end up with a 2 times an h plus, because our function is x squared. So for this particular function, that's just what it ends up being. Plus 2h plus h squared. And see how the middle term you get twice? So you have the 1 squared, you have the second one squared, and then whatever the 2 multiply together to get, you have double that amount. So there's a trick to kind of do that without having to multiply all that out. When you're squaring a binomial, you square each one and double what they are together, then you get your 3 terms. So really, we could say a little bit more specific what that y value is, but all we're going to do is we're going to find an average slope. We're going to find the slope between that, what color point do I have going there? Like a aqua? What color do I have going? Like a bluish green? Just bluish? Okay, well, that bluish, we'll call it. So my bluish point and my black point, we're going to find the average slope there. So what I'm going to do is we're going to say my y value, which I'll start off, just say f of 2 plus h minus my first y value, which is, I'll just say 4. And then we'll do the same with our bottom. We'll do 2 plus h minus 2. All that is slope, right? The only difference here is we're going to change this to a limit as the 2 points approach each other. So what's changing here? There is no x yet. Sorry. What's changing as those two get closer and closer? You writing in pen?
Yes.
Well, x could be really close to an h, so you might be able to change that easy enough. As h gets close to 0. And that's what that worksheet was on. Then I'll pull up really quick here again. This is a limit. As those 2 points get closer and closer together, so as these 2 points here got closer and closer together, that extra little bit was getting smaller and smaller, getting closer to 0. And that's kind of what we did here. We said, okay, so A is just a little bit bigger here. Oh, it won't let me write on it. A is just a little bit bigger there. As it was getting closer and closer, it was nothing. And you look down, I even wrote down the limit, or as A is approaching 0, some of you guys figured out that was going to be 64. That's the same thing that's going on in this particular picture. 2, 4. Which, all we're going to do is simplify this and take our limit, and we'll see kind of what happens. Hopefully we're able to do that. We've already said what that equals. We already multiplied all that out. If you plug that in and take that and square it, we get 4 plus 4h plus h squared. On the bottom we have 2 plus h minus 2. This is still the limit as, and I wrote down x again, just an old habit. As h approaches 0, 4 minus 4, 2 minus 2. When you plug in h right now, what happens? You get 0 on the bottom. Can't do that. Most of the ones that we're going to do, those constants on the top will end up canceling. Because when you plug in the value in the first and second, it's going to end up being the same. It's going to cancel. And the only thing we end up with on the top is h, which means, can I just cancel that? Yeah, so if we cancel an h, but what I'm saying is we'll have an h in every term so that I can actually factor that out. And if I can't, there's going to be some other trick we're going to have to look at to try to make that work. Factor out an h and cancel it. Sometimes limits are easy. Sometimes they can be made easy. Here it wasn't easy, but it can be made easy. We can get that to simplify, to reduce to a place where, hey, now plug in 0. What do we get? 4. Which, do you remember what we were finding? The slope. Our tangent slope equals 4. Is that all they wanted? Write an equation for the tangent to the parabola at this point, which is really easy if we know point slope form, because we just do y minus our y value equals our slope times x minus our x value. There's our answer. That's our tangent equation. That's the equation of the tangent line. Can we handle that? That's like the first time, that's the second time we've actually done that, because we did that earlier. Maybe it'll get easier as we go. Kind of get the hang of it. Ready to try again? Oh, yes. Oh, yes. That was intense. Actually, circuses are intense. This is in a classroom. That's hilarious. The limit as I'm never going to get past writing down x. As h approaches 0, of f of x plus h minus f of x all over h. That's your tangent slope. It's also your instantaneous rate of change. students often find one of the most difficult parts of this is all the different ways that they're asked to do kind of the same thing. So when they ask for the tangent slope, the instantaneous rate of change, the slope at a specific point, all of those things are asking for that same concept, of just how we're going to apply it. Now I know some students are gone, so I'll probably just do one more with you. Kind of that same idea. And we'll just use this, which you can just memorize it. If you haven't understood like how the 2 points are getting closer, how that limit gets you the slope or that exact slope at that point, fine. Then ask again in a couple weeks when we've done it for a while and maybe it'll click then. But right now, then just know that this will get you it. This is what that is doing. That was all the y. This is the equation that we can use to get our slope at an instant. What's the equation we use for average slope or average rate of change or our secant slope? You're thinking of something else. That's for something else. You just use your slope formula. y2 minus y1. So if you want an average rate of change, you want your secant slope, you just use your slope formula that you've always used between the 2 points. If you want it at an instant, at a specific time or a specific point, use this guy. All right, find the slope of the curve at a specific point. So we have to know, this is asking slope at a specific point. One more. This is where we'll do this one, and since we're missing some folks, we'll say, try not to get any further ahead. I'll let you guys try some of the homework and jump on that. Slope at a specific point. So what are we doing? Need a lot of room then. We're going to do the limit as h approaches 0 for f of x plus h minus f of x. So you have your function's output and then a little bit more than that, which is the plus h. You guys okay? You guys okay? And does it make sense why that's the top there? You have your two y values. You see the first one I wrote down is just a little bit bigger than the second one, a little bit further to the right than the second one, almost like we have that shift. And then we end up actually with x plus h minus x, but those x's always cancel, and you just end up with h on the bottom. So that's why it doesn't exactly look like a slope formula, because the x minus x in the bottom is always canceling out, so why keep writing it down? Okay, this is kind of challenging for some. Rewrite this. The limit is still there. Maybe we won't write that every time, but for now we'll keep writing it so we remember that we're taking the limit as those two get closer and closer together. What's f of x plus h? Yeah, good. It's 1 over x plus h. So I know that she's got it. Somebody else tell me where she's getting that from. Why is it 1 over x plus h? What is she doing? So then I know two people got it at least. Yeah, she just plugged it into that thing. Isn't that how you find f of like 3? You plug in 3, right? F of 4, you plug in 4. So f of x plus h, you plug in x plus h. So all we did was we plugged in x plus h into the x. And now instead of 1 over x, we have 1 over x plus h. We know what f of x is. That's it. That's your limit. If you can find me that limit, you're done. What happens when you start to find the limit? You get something over 0, which is not possible. So now we're thinking, okay, we've got to try to simplify that. So what can we do to try to simplify that? Subtract the fractions, which means we need a common denominator, which is why we reviewed all of that, combining those types of complex numbers or complex fractions where you have all that. So what's our common denominator? X times x plus h. And because this is one of the first times we're doing this, instead of just kind of writing all over that and making a mess of it, I'm going to go ahead and just rewrite the whole thing to make sure everyone's following it. But I have been pretty impressed with how well you guys have remembered all of the fraction stuff with some of those variables. So what do we multiply the first one by? X, so do that to the top and bottom. Multiply the second one by x plus h, so do that to the top and bottom. As you do this more and more and you get to see some of these things, you'll recognize that, okay, that's going to be that one minus that one, and maybe that goes a little quicker. You start doing some of that in your head. Don't forget. We're still just trying to do this limit. I'm just kind of getting tired of rewriting it already. Because every time I go, I'd have to technically rewrite the limit as h approaches 0. We're doing so when we get to the very end, just don't forget. We still have that there. I'm just getting sick of writing it after a couple already. Okay, so what does that equal? Close. I'll give somebody a sucker if they can give me the right answer. I have suckers. I'll grab one. Somebody gets a sucker if they can give me the right answer. That's really, really, really close, but not perfect. Kick it over. But yes, okay. All right, genius question of the day. We do not get h. What do we get?
Get h over.
Nope. When you subtract those two fractions on the top, you do not get h over x times x plus h.
X minus x.
Really want to give away the sucker. Natasha, come on, you got this. What do we get? You're thinking h, right? No? Yes? Okay, I'll give a sucker if you can tell me why we get negative h. That should be everybody, though. You're subtracting it, right? So don't forget you're subtracting that entire thing. Wow, that's just like your algebra stuff here. You know what? I'll come up with a chance to redeem yourselves. Chance to redeem yourselves at some point. You guys okay with the negative h? All right, so just a little bit of algebra. Be careful. What's going to happen? We have a fraction over a fraction, so we can flip and multiply, which
-1.
cancel out. So we get, okay, all right, sucker. -1 over x times x plus h. Can I plug in 0 yet? So at any point you realize, wait, we can plug in 0 and no longer get that, we can go back and say, don't forget, really this whole time, we wanted the limit, right? So the limit as x approaches 0 for 1 over...
Don't forget.
Don't forget.
Bring your pad.
Well, shoot, how many limits have we done? And it's always x is approaching. It's still negative. And we're going to plug in 0 now because sometimes limits are as easy as plugging in 0. What do we end up with? -1 over x squared, which can give us any specific point we want a slope at now. We can get it in like 2 seconds. So for this particular function, what's the slope at x equals 2? -1/4. What's the slope at x equals 1? So this not only gets us to that slope at that specific point, but if we don't plug anything, now we could have plugged in the point we wanted a long time ago, and it might have made our simplifying easier. But if we wait till the very end, we have something that'll give us the slope at any point whenever we want. Well, and wherever we want. And that was A. So let's come all the way back, answer these 3 questions. This is going to go quick. A, find the slope when x equals A, then what would it be? Well, you'd plug in A. So whatever you get, that would be A. B, where does the slope equal -1/4? At x equals 2, because you plugged in 2, you get -1/4. What happens to the tangent to the curve at the point 1 over A and 1 over A? For different values of A. Okay, well, this is it's just mind blowing. Okay, come on, just settle down. It's not that bad. That's what we just looked at. Our function's 1 over x. So they're saying for different values that you plug into x instead of, they're saying A and 1 over A. So for different values, what happens to our tangent? Smaller fraction. So as we go to the right, what happens? Okay, well, let's just look at our graph. If we know this is a slope, no, I don't have a graph. Is your slope going to get bigger or smaller as we go further to the right? Smaller. And is it going to get bigger or smaller as we go to the left? Bigger. So we can know the slope at those specific points. We could talk about those slopes. What happens to the tangent to the curve at point for different values? as we could say, like, as a approaches infinity, our slope approaches, what happens to our slope? Okay, it approaches 0. As a approaches negative infinity, or it gets bigger, you could say this a lot of different ways. It's just, to me, less to write down, saying gets bigger and gets smaller. So it gets really, really negative infinity. What would we be approaching? Would it? We have negative, it'd be, wouldn't it still just be 0? What about as a approaches 0? Then it would be, our slope would be approaching, well, shoot, from the right side, what would it be approaching? So if a was positive, look at, we've got this right here, 1 over a squared. It's negative now, of something positive squared is still positive, right? So then we'd have negative over positive, which would be approaching negative infinity. All that limit stuff. And actually, because we're squaring it, from the left would be a positive, a negative or a positive, get negative infinity too. Means we must have something that looks like approaches negative infinity from both sides, approaches 0 there. They didn't ask for that. That's just for thinking. Okay, let's stop there because we're at 26 minutes of fun time already. And I'll stop this and